some highlights of the discussions today were we discussed line integrals, of vector fields. So the structure we discussed were the form work done by a force field F vector along a curve C. So the work is integral over the curve C of F dot product with dr, which is can also be denoted as integral over C of P dx plus Q dy plus R dz, where P, Q, and R are the three components of the force field F vector. Okay, so and the curve C is given by x equals to x of t. This is given. Y equals to y of t. Z equals to z of t. And t varies from A to B. So the main idea here, when we calculate the line integral of a vector field, when we calculate this, we convert this line integral into a normal calculus 1 type integral. So this would be integral from A to B of something times dt. And that something can be obtained by replace getting formulas for p in terms of t, because p depends on x, y, z. And via x, y, z, p depends on t. Px is x prime of t dt as a differential. Again, q depends on x, y, z, right? Q depends on x, y, and z. And again, third, x, y, z depends on t, so ultimately q depends on t, and dy is y prime of t dt. So everything depends on t here, and whatever we get here, we get a function of t dt, and we calculate it like a normal calculus 1 type integral. So let's provide the first example. Let's see. Let's calculate the work, the following line integral. Integral over c of minus 2xy dx plus z dy minus x dz. Well, the curve C is given by x equals to t, y equals to 2t, z equals to 3t, and t is from 0 to 9. So let's calculate this line integral. Okay? So like I said, convert everything into an integral from 0 to 1 by replacing everything in terms of t. We know x, we know y, we know z. We know dx, we know dy, we know dz. So dx is dt, dy is 2dt, dz is 3dt. Differential is derivative times dt for all functions. So w will be integral from 0 to 1. So we convert the line integral ultimately to an integral from 0 to 1, where 0 and 1 are the limits of the domain of definition of the curve space curve C. So integral from 0 to 1 of, let's put a bracket here, then dt in the end. So now let's replace everything here in terms of t and ultimately give dt as a kind of common factor. Let's write minus 2xy. So minus 2 times x is t times y is 2t times dx is 1 dt. So put times 1 so we to have an idea where does it come from, plus z is 3t, dy is 2 dt. 2 dt is dy. Minus x, so minus t times dz is 3 dt. Right. And that will be integral from 0 to 1 minus 4t squared plus 6t minus 3t is plus 3t dt. That will be minus 4 over 3 t cubed plus 3 over 2 t squared from 0 to 1. That will be 3 over 2 minus 4 over 3. That will be 9 minus 8 is 1 over 6. So, in other words, the work done by the force field, what force field? This force field is minus 2xy, z, and minus 6. So the work done by this force field along the curve C is 1 over 6. So there's a general idea to calculate line integrals of vector fields over space or plane curve. This also works for plane curve. Okay. A special case is when the force field to integrate is a gradient field. So this will bring us to fundamental theorem of calculus 3, FTC 3. So what's the idea here? According to FTC 3, the line integral over the curve C of f dr, dot product dr, is assuming that the force field to integrate is the gradient of some scalar field T, the big ask, so to say, because not every vector field is a gradient field, but if it is a gradient field, this line integral will be the phi between initial point of the curve and the terminal point of the curve. That means phi of terminal point of the curve minus phi, the value of the potential at the initial point of the curve. In other words, the space cap C joins a point called init with another point called term, and doesn't matter how we get from initial to terminal. So we only care about the value of the potential at the terminal point minus the value of the potential initial point. So it's path independent, right? Because it doesn't matter which curve we choose from, smooth curve we choose from initial to terminal, we get the same difference because the same potential at the terminal point of the curve minus the value of the potential at the initial point of the curve. Okay, so let's try to provide an example. Let's find the line integral over C of the following. 2y squared dx, then plus, plus 4xy minus 3y squared z dy, then minus y cubed dz. Where C is a curve which joins 1, 1, 1, that's the initial point, to 1, 2, 3, there's the terminal point. So the curve C joins 1, 1, 1 with a point 1, 2, 3. And then calculate the line integral of this vector field with components 2y squared, 4xy minus 3y squared z, and minus y cubed. Clearly, when we are not given particulars about the curve C and we are only given initial and terminal, clearly FTC3 is to be thought. Solution here. Step 1, find the potential for the vector field F. Find the potential for F vector field. In this case, read the coefficients of dx, dy, dz. The vector field under discussion is 2y squared, 4xy minus 3y squared z, minus y cubed. To find the potential. So what does it mean? dp over dx should be 2y squared. dp over dy should be 4xy minus 3y squared z. And finally, dt over dz should be minus y cubed. So let's try to find enough information from these three to figure out the potential phi. So from the first relation, by integrating the x variable, phi will be 2xy squared plus a constant c which depends on y and z. From the second relation, by integrating the y variable, phi will be 2xy squared in the integral of the first one minus y cubed z plus another constant is plus d of x and z. And thirdly, integrate the z variable, so phi will be minus y cubed z plus a constant e of x and y. So now let's take these three pieces of information and the three pieces of puzzle and find the potential phi. Phi will be 2xy squared minus y cubed z plus a constant c, but we don't really care too much about the constant because anyway it gets subtracted when we do phi from init term. So that's a potential for the vector field which appears in this integral. Okay, so let's apply the FTC3 theorem. Now that we got the potential, we are ready to apply FTC3. This being the potential, we continue. This line integral equals to, according to FTC3, the potential, which is 2x y squared minus y cubed z. That's the potential P between initial point of the curve, and terminal point of the curve. Like we consider a curve, if you remember, from going from 1, 1, 1 to 1, 2, 3. Okay? So let's see what will be the difference. Let's introduce two spaces here. Here vary the term, here we put the value of the init. So the terminal point will get terminals 1, 2, 3. Init. So maybe even better we replace term with 1, 2, 3. Init with 1, 1, 1. That's better. 2x y squared. At the terminal point, this will be an 8 minus 8 times 3 is 24. So that's what it is. What is this function, the potential at the terminal point? The potential at the initial point will get 2 minus 1 is 1. So the result of this problem is minus 16 from the first parenthesis here, minus 1 will be minus 7. Okay. And the third important thing we discussed today was Green's theorem. One of the major theorems of vector calculus, which is the junior of the system of three major theorems. So Green's theorem. So Green's theorem applies to line integral over a simple closed curve C. So let's imagine a curve C oriented counterclockwise. There's the curve C. And C is the boundary. That's how we know the boundary of a plane domain D. This D. Green's theorem says the line integral over C of P dx plus Q dy So the line integral over a simple closed curve, which is the boundary of the plane domain D, is the double integral over D of dq partial derivative of q with respect to x minus partial derivative of p with respect to y dA. So basically, Green theorem transforms the line integral into a double integral. So that's one important feature which appear in a formal manner in all three major theorems of vector calculus. Okay, so let's do an easy application of Green theorem. Okay, so let's see. Exercise 3. Let's consider curve C, which will be the circle, unit circle counterclockwise. So x equals to cos t, y equals to sin t, and the t is from 0 to pi. And that would be unit circle oriented counterclockwise. Let's see. B, C is the boundary of the unit disk, right? So let's calculate integral over the unit circle of the following. Y plus sin cube x. I don't recall the example we did today in class, but it's very similar. Y plus sin cube x dx plus 2x plus y to the power 5 dy. Okay, so let's use Green theorem to evaluate this line integral. Let's move on. So according to Green theorem, this will be a double integral over the unit disk P of this is P and this is Q. So dq over dx minus dq over dy dA. That will be double integral over d dq over dx. dq over dx is just 2 minus dp over dy, because sin cube x does not depend on y, is just 1. And we get double integral over d of dA, and the double integral over d of dA is just the area of the plane domain D. So in this case, the area of the unit disk equals to pi. Okay, so a couple of more things. The last couple of things we discussed today was how to use Green theorem to find 3 nice formulas to calculate the area of the simple domain D in the plane. So again, in the plane we have a domain D, and the C is the boundary of D. Area of D has 3 important formulas. Integral over the boundary of D of minus y dx, integral over the boundary of D of x dy, and also integral over the boundary of D 1/2 in front minus y dx plus x dy, according to Green theorem. So, for example, in the last example, P is minus y over 2 and Q equals to x over 2. In this case, dq over dx minus dp over dy is 1 over 2 minus 1 over 2 is 1. So we are about to integrate double integral over d of dA, which will be the area of D in all cases. Okay, so that's basically an overview of what it